Hey, Earth Science students, welcome back. Welcome back to your next video lecture. Hopefully you've enjoyed these. Hopefully you are appreciating the benefit that they have, working at your own pace, taking a break when you get bored or tired or sleepy, working around your own schedule and that kind of stuff. And then the added benefit is in the classroom. We don't have the long lectures going on. We are just focusing on doing activities to help learn. But again, welcome back. Hope everything's going well with you. You're having a great, what should be weekend. But hey, again, thank you for watching this video. Man, we got some great stuff today. I mean, we have got some great stuff. Love talking about this stuff. As you can see, man, we're going to be talking about this relationship between the sun, moon, earth, all that stuff. I mean, we're going to look at eclipses. We're going to look at seasons. We're going to look at calendars, clocks. I mean, we're going to explain a lot of things that go on with the earth, or on the earth, I should say, and kind of get a big picture explanation of what's really going on, what's causing it, what's making it happen, all that great stuff. And this is going to be some fun stuff once we get in the classroom. I mean, when we're working with eclipses and looking at eclipses and talking about schedules and calendars and all that stuff, it's going to be just a great time. But enough about that. Let's get this thing going. But again, thank you. And again, hope everything is going well with you. Everybody is safe and sound. And by the time we watch this, let me think. First week, we're just getting set up. Second week, look at my list here. Second week, the EMS scale and all the wavelength and stuff. And then that next week, just talking about the moon and things like that. And so by the time we get done, time you watch this and we talk about everything that we're going to talk about with this stuff in the classroom, I mean, we're about 5 weeks in. So we're looking, into September-ish by the time this is done. So, hey, it's moving right along. Hopefully nothing has happened to interrupt the school year, but who knows? Who knows? All right, well, this video is going to be designed to be an hour long, but that's also supposed to include the amount of time that you need to pause and write things down. So I'm going to try to keep it in that 40-minute range, but I don't know. There's a lot of stuff and a lot of cool stuff, a lot of stuff I like talking about. So we'll see what's going on. If it gets too long, what we can do then possibly is break it up into a couple of them and watch the first part on one weekend and the second part on the next weekend. But we'll just see how it goes and take it from there. But again, just a reminder, part of your homework, and I do the air quote things every time I say the word homework, is you get points for the notes. So if you take a good full set of notes, you get all the points. No, excuse me. And if you just do half, you get 50%, and so on and so forth. So be sure you do your due diligence, take your time, and get everything drawn out, written down, and all that kind of good stuff. So I'll always mention what I'd like you to draw and write down. And by writing it down, by drawing it out, it's only going to help you to reinforce the learning part of it. So let's get started. And in this first part, you can see I've got I got 5 images here that are going to help us to kind of explain rotation. When I was a kid in your age, it was called rotation, revelation. Those words, both with R, so it kind of made it more of a challenge to students to remember which was which. You don't hear the word revelation so much anymore. Now you hear the word orbit, which makes more sense. Plus it separates the words. So we're going to talk about the length of time that the Earth orbits the Sun and the length of time that it rotates on its own axis. And those numbers, you're familiar with the numbers because they create or the time span for other things, calendars and clocks and that kind of stuff. So it'll all kind of tie in and make some sense here. So this first diagram, let me get a pen here, and we're Earth Science, so we'll use this green right here. So we're going to look at this first diagram right here. So you just want to do, and I know it'll be tedious, but you just kind of draw this out. It's not so much that you need the X and Y axis; they're just helpful for landmarks. But certainly draw your circle, label your dates, put your little dot on there, whether it's red, doesn't matter. Just some kind of dot, and got the Sun. And as it says right here, and you don't necessarily have to write this, just as long as you know it, that these dots or these points is where the Earth is as it goes around, okay, the Sun. And you can see that based on the dates, we're going this direction. So we're January, February, March, April, May, June, July, August, September, October, November, and then back to December. And then once we get back to January 4th, which is an important day, January 4th is, because that's my birthday. It just so happened that that's on there. That's my birthday, yeah, January 4th. So all my life, I've gotten to celebrate my birthday by going back to school after Christmas break. So that's always been a fun experience. And many years, both as a student and a teacher, that first day back is the birthday. So there you go. Fun times. All right, so it takes approximately 365 days and of course writing with the mouse is always fun. It takes 365 days for the Earth to go around or to orbit the Sun, and that should be a familiar number to you because that's how many days in our calendar, and that's what the calendar is based upon, the fact that how many times or how long it takes for the Earth to go around the Sun. And that's why our seasons are kind of typically the same, heat, cold, that kind of stuff, because we're kind of in that same spot at that same time of the year in relationship to the Sun. So 365 days go around the Sun, and that's what establishes our calendar. Now, the other one, this picture, is we're going to talk about the length of time that it takes for the Earth to rotate around its axis. And this, of course, is an axis right here. And that's that right there. That's what that red line represents. And you can see that we're also going this way. So not only when it's going around this way, it's also spinning in the same direction as well. And once we get into weather, this rotation, okay, with this tilt causes a lot of things. But we'll talk about that once we get to weather and stuff. But our stuff like prevailing winds and all that stuff, unequal heating. But we'll talk about all that stuff in its time. But excuse me. All right, now for the rotation, it takes 24 hours approximately for the Earth to spin on its axis. Okay, and again, that number should be familiar to you because that's how long we call our day. So the reason why the clock is kind of set up in a 24-hour time span is because that's how long it takes the Earth to rotate on its axis. And so when it gets, so that's why kind of midnight is always kind of the same darkness level, noon always kind of the same light level, because we're at the same spot on our rotation, okay, that at that same time every day. So 365 days to go around the sun, that kind of sets our calendar, and 24 hours to go around on its axis, and that kind of sets our day as far as the length of time. Alright, so we've established their orbit, time, and length. We've established the rotation, time, and length. But because those things are happening simultaneously, that causes causes isn't the right word, but well, I'm going to use it anyway because I can't think of a better one. A lot of things to happen. The third variable that we're going to interject is the fact that the Earth is not straight up and down. Okay, in relationship to the continents and everything, it's got a slight tilt. Now you may say, well, what do you mean it's not straight up and down? There's whatever the top is, that should be the top. True, but based on the magnetic pull, okay, what we consider true north, okay, because of the pull, is not straight up at the very, very top. There is a slight tilt, and you can see the number way over here, but that's kind of small, so I'm also going to write it here. And that's the degree symbol, okay, as in, like if in a little bit bigger dot there. So if you were, when I say degrees, if I were just to kind of draw a circle, and this isn't going to be a great circle, remember the old geometry, 90 degrees, and then this is the old 180. Okay, and then you got 270 over here, and then either back, back to the 0 or 360 if you go all the way around. Okay, so if this is 90, then that means this is 45, and so roughly half of that would be 23.5. Oh, that should be a 2. So approximately there. So that's approximate. That's the tilt. But because it's tilted and also spinning on its axis and also orbiting around the sun, that's what generates our seasons. Okay, our 4 seasons. And so that's what we're gonna talk about now, using this diagram here, and actually all 3 of these. But this is the main teaching one, and these will just emphasize or highlight the material. Excuse me again. Alright, so if you can imagine, okay, and if I'm sure your social studies skills are strong, but just in case they're not, this is us right here. So like this is North America and Canada, and this is obviously Central America, and this is obviously Florida right here. And so if you were to try to estimate where we are, it's approximately, I'm going to say right in there. It's approximately where we are. That may be a little high, but that's the general idea of where we are. So, if you can imagine, as we rotate on our axis and we orbit the sun, the angle that we are to the sun changes. Okay? And because of that, that causes our seasons. So there are some times, and you can see it would be here. So this is also, this is South America right here. So this is us right here. And when the Earth would spin, okay, when we get to this side facing the sun, we would be right here, almost directly pointing at the sun. Okay, and that's what causes our high temperatures in the summer. Okay, but as we, so you can kind of see the tilt, pushes the top more towards the sun, and that's what puts us into our summer. But with the tilt, okay, we'll go this way. Okay, so now again, we're right here, and because now the tilt has changed in comparison, and you can see this arrow that we're going around, and we also talked about it over here, we're going in this direction. Okay, now with the tilt, as we rotate on our axis and orbit the sun, okay, our angle towards the sun changes. And when we get in the classroom, or when we're in the classroom, we'll use models to kind of showcase this. We'll literally have one of you, or I'll do it, whatever. We'll have something that represents the sun in the middle of the room, and then with the globe, in the tilt, we will move it to these 4 positions around, and you can see that tilt changing our angle. So that'll make it more visual for you, but we'll explain it today. So when the angle and the rotation and the orbit all get us into this position, okay, now we're in September, so we start to cool off, okay, because we're tilting away from the sun. And as we move around, now we're in December, and we know what our December temperature is like, and you can see now that the tilt has the top facing away from the sun at its furthest point. So now when we're here, okay, we are no longer directly, that's not a good line, we're no longer directly pointing at the middle of the sun. Okay, we are now at a very steep angle away from the sun, so we're much cooler. And it's not that we're further away from the sun as far as distance, and that's why we're cooler. We are cooler because we are more angled away from the sun. But we all know that even in December, you can have a nice temperature day. You can get a 60-degree day in December or January, but you can also get a 5-degree day or a 0 with wind chill factor. So the tilt kind of causes the seasons, but the daily variation in temperature, where you can have a warm day, cold day, there's other factors at play, and when we get to weather, we will talk about that. But the prevailing winds, the moisture levels, there's a lot of other things that are contributing to the daily temperature. What we're focusing on, what we're talking about, is the season overall. That December to February, that September to November, the March to May, those kind of seasonal times. We can all agree that the summertime is the warmest overall, and in the spring and fall are somewhat similar in temperature numbers, and they're both lower than summertime. And in winter, while it still may have nice days, its overall temperature is typically the lowest part of the year. So, and then again, as we continue our orbit around the sun and in our daily rotation, something else. Well, let me finish this and then I'll go back to that. So now again, the angle or the tilt has the top still not pointing to the sun, but it's angling back. So basically we point right at the sun, we tilt away, we're our farthest away, and now the tilt kind of brings us back towards. So we're constantly moving towards pointing at the sun and moving away from pointing at the sun. And so that's that. So let me go back. So I'll come back and finish all this, but because I did just think of something back over here. Obviously I should have mentioned it, and you're well aware of this as well, but because we do rotate on our axis, that's also what causes the day-night, that's not a D, Try that again. Day-night stuff. So when it's nighttime here, that's just because on our rotation of our axis, we're on the opposite side away from the sun. So all right, so back to the seasons and stuff. I'm going to close out the ink tray. No, I don't need to, because my original picture here is a little fuzzy, and so these names and dates are kind of difficult to see, but they're down here as well, and the dates are super clear to see. Alright, so but we are going to focus on this diagram now. Okay, so this diagram kind of showcases where the direct sunlight is in comparison to us, to kind of showcase these seasons. So we're in spring. So again, this is us right here, and right here, and right here, and right here. Now these pictures are kind of extreme. They're just showcasing the angles, and what they're not showcasing so much is the actual tilt. What they are showing you what our angle looks like compared to the sun. So we're going to start over here in summer. Okay, you can see, and when we do summer, it's this one right here. Okay, but what it's showcasing you is the fact that the angle that we're in, we're pointed more directly at the sun. Okay, to get that warmer. And in winter, okay, over here, we're tilted away from the sun, and therefore we get those winter temperatures. Both spring and fall, autumn. So when we're at, and it'd be this position right here, September, we're pointed in such a way that we're having fall, whereas South America is having spring, because they are lower than us, and so they're a little different angle. And then in March, which is this one right here, we are having spring, and they're having fall, or what they would consider fall. Alright, so just a reminder, we are looking at all the variables that cause these situations to happen. We're including the orbit, the rotation on our axis, and the tilt to describe the changes in the seasons. And now as we move to this one down here, they're up here as well, but they're fuzzy, it's hard to see. These are the solstice and equinox date ranges. So when we're talking winter solstice, what that means is that it's the time period in the winter time when the day, whatever day it occurs, it's the shortest amount of light. Okay, the shortest amount of light, and it's simply because we are tilted away from the sun when we rotate. So we're going to get a pretty short day. I mean, we're talking dark by 5-ish. Okay, almost 5-ish, 5:30 in there somewhere. And then when we have our summer solstice, okay, that's the day, whatever day it falls on, where we have the most light, or the longest light. And so it may not get dark until almost 9:45, 10 o'clock to be fully dark. That's why on July 4th, when you're waiting around, of course we didn't get to do it so much this year, but when you're waiting around for that fireworks show, it's 9:30, it's 9:45 before they can really start doing stuff, because they just need that full darkness to illustrate or illuminate, so the fireworks really stand out. And then the vernal, which is spring, and autumn equinoxes, those are the day that they're right in the middle. Okay, so they are, it's basically right at 12 and 12. Okay, we get half sunlight, half daylight, half darkness, I should say. Said light twice. But basically it's 12 and 12. So if the sun comes up at 6, it's setting at 6. So the length, so for the winter solstice, the shortest day, it isn't a huge separation. It's actually more like in the autumn, in the equinox, it's more like 7 and 7. And so it'll roll back to 5-ish, and then roll down to 9, 9:30, 9:45 as the time span. So all that said, what we looked at is the way that the orbit of the sun, we're going around the sun, the rotation on our axis, the tilt that the Earth has, all that, how it creates our seasons, our time changes, and all that stuff. So hopefully you took the time to write all that down. If you didn't, be sure you do before you move on. Whatever works best for you. Just make sure you capture everything. Some people might like to watch it all, get it soaked in, and then go back and write. It's entirely up to you to do it. This is, however is best for you, just as long as you do get it taken care of. All right. So with that, let me close the ink tray, and we will slide down and talk about our next topic. If I had to pick my five favorite topics in earth science, this right here would be in that list, the phases of the moon. I don't know what it is, but man, I love talking about the phases of the moon. I like talking about the seasons and the time changes and the orbit and rotation stuff. That's some pretty cool. That's some big picture stuff. Those orbits and rotations and how that causes the seasons and our calendar and the time and everything. But the phases of the moon, I don't know what it is. I like looking at the moon each night, and when you can see it during the day, and checking out those phases. Now I don't tie a lot into the old full moon, Friday the 13th kind of stuff. That makes for great movies and talk, but I do like looking at the phases of the moon and talking about the phases of the moon. So it'll be pretty exciting times when we're talking about this stuff. And of course, as you know, if we haven't already started, we should have started. But anyway, we will be documenting the phases of the moon, and we'll look at the daily moon phase, not simulation, but interactive, showing you so you can see what's kind of got going on there. All right, so phases of the moon. But first, we got to set some vocab words, and where's the best spot to circle? So I'm gonna go with this middle one right here. So the first word we got to talk about. Oh, I didn't mean to do that. I need my ink tray up. The first word we're going to talk about is waxing. So, see, is it better to draw this? Maybe it's better to type it. Let me just type it. Move this box. That's where it's kind of clear. So, I gotta move my notepad here and pull my keyboard back to me a little bit. So that's the sounds that you're hearing. All right. Waxing. Okay, so waxing refers to this idea of the light on the right-hand side of the moon as we're seeing it. So it's basically the idea of spreading car wax. And I don't know if that's even a thing anymore. When I was a kid, it was important, but cars were made out of, and trucks were made of actual metal, steel. And so you had to wax it to keep the water from staying on it and rusting it. Now most everything is plastic, and that isn't the case anymore. But the waxing refers to the light being on the right hand side of the moon. Okay, so that's waxing. The other word, and it's right here, waning, refers to, oh, I put the word to in there, I don't need that. As I said it, that's why I did that. Alright, now we're good. Dark being on the right hand side of the moon. Okay, our next word to talk about, and we're going to say that it's crescent. It's here, it's here, it's here, and you can see the pattern. Okay, so crescent refers to small portion of light on the moon. Okay, small portion. Oh, I forgot the word portion. Small portion of light on the moon. So you can see crescent here. You can see crescent here. You can see crescent over here and over here. So that's crescent. Okay, small portion of light on the moon. Okay, the next word we're going to talk about, it's here, quarter. So you got quarter here, quarter. And that refers to the half moon half the moon is lit up as we can see it. Okay, so when we're looking at the moon face, half of it is lit up. Now you may think, well, if it's half the moon is lit up, why don't we call it half instead of quarter, which would be 1/4? And that's a great question if you were asking that. What you got to think of is, if I look at this face, if I look at this moon here, okay, I'm seeing half of the moon, and half of what I see is lit up. So what is half of a half? Okay, 1/4 or a quarter of it. So if I have a dollar bill, I can only see half of it. That represents 50 cents. And if half of that is lit up, that represents a quarter, and that's what's called a quarter. And again, when we're in the classroom and I'm holding up the model and you were looking at one half of it, okay, that will make more sense when half of the half is lit up. But you'll see that, and it'll be perfectly clear. Okay, the next word, or actually it's the last word too, gibbous. And that refers to more than half the moon is lit up, and typically it's 3/4. So like you can see gibbous here. Excuse me. So like this would be a half, so we're about 3/4, and gibbous over here 3/4. Okay. So the idea is that waxing and waning refers to darkness or light being on the right hand side of the moon as we're seeing it. And then crescent, quarter, and gibbous tell us how much of the light is illuminated. So when I'm looking at a waxing gibbous, and I'm done typing, so I'm going to close that and get my ink back up here. So if I'm looking at waxing gibbous, okay, waxing tells me that the right hand side of the moon is bright or lit up. Gibbous tells me that that light extends out to 3/4, okay, or more, certainly more than half. Okay, so when I'm looking at a waning gibbous, okay, the waning tells me, hey, a portion of the right hand side is dark. Okay, and gibbous tells me that the light extends out, more than half and approximately 3/4 or 75%. But the dark part is on the right. Okay, when I look at waning crescent, again, waning tells me the right hand side is dark, and crescent tells me that only, a small portion of the moon is lit up, and because it's waning, that light's going to be on the left hand side. Waxing, crescent, waxing tells me the light is on the right hand side, and crescent tells me that it's only a small area of light. So that's the names of the phases of the moon and the words associated with, and just by seeing the name of the phase, you can picture in your mind, okay, if it's waxing or waning, you can picture where the light is on the moon. And now we're looking at, when you get the second word, gibbous, quarter, or crescent, that tells you how much of the moon is lit up. So that's the idea of the phases of the moon and what we have here, and now we can look at the diagrams. So I'm going to start here. Okay, so it doesn't matter where you want to start. Say we'll start here at the full moon. Okay, but we want to look at is what's causing. Okay, so what's causing these shadows? Now, if you can imagine, Earth is in here, and based on what we're seeing, can you determine where the sun is? Okay, and I'm sure some of you said, oh, I bet the sun is over here, because these are all lit up, okay, and some of these are not, but that would not be the case. Okay, if the sun was here, this part, okay, if the sun was here, then what would be here would be dark. Okay, so the sun is not right there. If this side is lit up, where does the sun have to be? Yeah, it's got to be over here, okay, shining. Okay, and then now this stuff is lit up, and the reason why this is dark to us is because the sun's here, and that's why this is lit up, okay, and this is lit up, lit up, lit up, lit up, and now it's getting to where being blocked. So that's the phases of the moon, and this is kind of and all these are kind of the same. New moon, waxing crescent, and kind of in each, and this is what it looks like as it rotates through. Waxing crescent, quarter, waxing gibbous, full, waning. Okay, wait a minute here. Wait. this chart here, alright, look at these names. I didn't notice this when I pulled this in, but that says waning, and the light is on the right. That says waxing, and it's dark on the right. So this chart here, for some reason, does not appear to be accurate. So we're going to discredit that and not look at that one. Yeah, because here we have waxing right hand side, waning, dark on the right. Yeah, so this one is right. Now, and this is what it looks like, kind of, if you took the different nights or different sections and in a row. So you've got the sun, the light moving across the moon, and then now the dark moving across the moon. And this takes, you can see here, I'm going to circle it here, and then we'll come back and talk more about the significance of that. But it takes about 30 days to go through the entire cycle. So if you have 1, 2, 3, 4, 5, 6, 7, if you got 7 phases and you've got 30 days, if you do that math, divide, carry the 1, all that good stuff, you get about 4 days, 4.5 days of each phase. So that's why there's not just one day that's a full moon. It's typically there's one day that it's the brightest full moon, but you get about 4 days of having a full moon. So it's kind of more of a cycle or a range than anything. All right, now back to this that I circled here, this number of days, and we're going to round that to a 30. Okay, so we talked about the reason why we see the same side of the moon all the time. Okay, so it takes about 30 days it takes about 30 days for the moon to go around the Earth, but we're also spinning, and that's kind of it's a general area of the month, but because it's rotating, we're rotating kind of the same speed, we're just emphasizing that. That's why we kind of always see the same side of it, because we're moving at the same speed, mostly. Not exactly identical, but it's pretty close. Alright, so we're going to close out this ink tray, and again, make sure you've written down the vocab word certainly. Make sure you've drawn the different moon phases, and make sure that you did not look at this chart here, since we have decided it is not good, and I'm not sure why that would be, why someone would do that or make that mistake, but anyway, not important. So make sure you've drawn them, make sure you've written down the vocab words, drawn you some diagrams, and get all that good information. So with that, let's slide down and talk about our last topics. And some great stuff here. Eclipses, man, I love talking about eclipses. Love it when they happen. Love going outside and watching them happen. Love watching the videos of them happening or after they've happened. Because sometimes, because of our position on the globe, we don't always get the best views of the eclipses. Sometimes, we're in the best viewing spot, but for the most part, we are not in the best viewing part. So it's fun, it's interesting. I shouldn't say not fun. Penny from Big Bang Theory would tell me that I used the word wrong, but it's interesting to see them from other locations, because then you get get a full, better view of how it looked. And sometimes when it happens, we're cloudy here, and it's not always easy to see. But we're going to work with, let me get my pen up here, we're going to look at this diagram here, and we're going to talk about tides. Okay, so another situation that is occurring because of the sun, moon, earth relationship, is tides. Now, in a 24-hour period, in other words, in our one rotation, okay, we're going to have high tides, we're going to have low tides, and we'll have those twice. So 2 sets. Oh, that F went bad right there. 2 sets of tides. Yeah, my mouse slipped on the mouse pad. 2 sets of tides. Well, that was bad right there. So you'll have 2 high tides, 2 low tides, and what's happening here as the Earth turns, in this direction, the water that is the closest, okay, to the sun is being pulled towards that. So, for example, when this side of the Earth, since the sun's right here, here's the sun, here, this is us. When this side of the Earth, the water is being pulled this way, yeah, that will be their high tide. And in the water, so if the water is being pulled this way, then over here we're going to have the low side, the low tide. And then then it just rotates around and it continues to switch. So the sun obviously is much, much larger than the moon and the earth too. So it's going to have a very strong gravitational pull. Excuse me. On the water, and it will pull it towards the sun. So on the opposite side of the earth is where they'll have the low tide. When you get a situation where now, but the moon, even though it's smaller, it's much, much closer, and it also has a gravitational pull on the water on Earth. That's why it moves in and out on those tides. So whichever side of the Earth is facing the sun, they're going to be in their high tide. And when it's also the situation where the moon is on the same side of the sun, or in other words, when we're facing a very dark moon, because it's in between, or in the time period where we might have a solar eclipse. Okay, you see a solar eclipse, that means they're on the same side, and the high tides will be even more so, will be increased, the high tide. Now when I flip, and these are the phases of the moon, so when the moon is over here, it's still pulling on the water, okay, and it's pulling on the same plane as the sun, so we're still going to get those high and low tides. They just won't be as extreme because it's not that the moon is pulling against the sun, it's just pulling in the opposite direction, so maybe that is against. So you still have your high tides, okay, it just won't be as much. So whatever side is facing the sun, the water will be pulled that way because the sun has a stronger, but the moon being on the opposite side would just reduce the high tides just slightly, okay, just slightly. Now when the moon gets to be here or here, okay, these are called spring tides when the moon and the sun are on the same plane, okay, on that same y-axis line. Okay, when the moon is on the this plane, so it would be on the y-axis. Now we're going to have neap tides, okay, because now the sun and moon are working at right angles of each other, basically pulling in a diagonal. So now you're going to end up having the lowest okay, the lowest of the high tides and low tides. It'll greatly even more reduce the effect that the sun has on the tides. But just another thing that is happening because of this rotation, orbit, and now we're throwing in the moon's orbit. Okay, as well. So that's the idea on tides. So neap tides, maybe I should let me jot all this down so you will know to do so as well. So let's start with spring tides. The moon and sun are both on the, and we'll call it the x-axis. And then on neap tides, we'll put sun x-axis, there we go, moon y-axis. Okay. And then of course, then also write down something about the high tide, low tide, and that information, and how the moon can increase the high and low tides or decrease the high and low tides based on its position. So if the moon and the sun are on the same side, you're going to have the highest high tide, lowest low tide, and then when the moon is on the opposite side, you'll still have high and low tides, but it'll be reduced. All right, let me close this, pull my pen back up. Actually, I need to close that, and let's pull this up so we can write and draw below. All right, these are our last two topics, the eclipse. Okay, the eclipse are named based on what's getting darkened. Okay, so in this case, the moon, okay, is getting darkened. So this is a lunar eclipse. And so, from our vantage point, in this case, the sun would be getting covered up. So this is a solar eclipse. All right, so it's all about shadows here. Okay, it's all about shadows. So we're going to talk about these two words here, umbra and penumbra. Okay, and this is probably best just to type it so it's clear. Oh, that didn't happen. All right, so let's start with umbra. I think that was a Pokemon character, but my son was into that, but for some reason that's coming up as a Pokemon character, but maybe not. Okay, so umbra is the direct, try that again, is the direct shade. And so you can kind of see in here that with the sun here, the earth here, and the moon here, this umbra is the dark shade. It's because the earth is blocking, okay, the sunlight from the sun. And over here, umbra, super smaller because the blocking object is much smaller. In this case, it's the moon. So the umbra is that direct shade Okay, the penumbra is the indirect. You could also say secondary. Secondary shade. It's that larger portion. Basically, if I take this line, this is the sunlight, so it's going to create this shadow here. And if I follow this line, no, it'd be this line. It's going to create that shadow. So, umbra, direct shade, penumbra, indirect. Penumbra is always a bit larger area, and of course it's based on if it's the Earth that's the blocking object or the Moon is the blocking object. All right, so lunar eclipse. So if you can imagine, let's see, the Moon orbits in this. Oh, I didn't mean to do that, so I'm going to get an ink tray here. If the Moon orbits the Earth in this circle, okay, so it's moving up into the shadow caused by the Earth. Now, what you got to remember, think about is if the sun's here, the Earth here, the Moon's here, that shadow is always there. It's just that we don't have anything to bounce off of. So, for example, when you're outside, based on if the sunlight's out, you always have a shadow. It's just sometimes, like if you're in the grass, you may not be able to see it because it doesn't have any solid object to be on. Or say you're in a glass room. Yeah, if you're in a glass room, you would have a shadow from the light if the lights were on. But because it's glass, you may not be able to see it. But if you were in a room made of wood, or you're standing on a wooden floor, or rug, whatever, then you could see your shadow. So the shadow's always there. It's just now the Moon, because it's orbiting the Earth, is going to move into that shadow. That's why eclipses don't last very long, because the Moon moves into the shadow, but it keeps on moving, and then it moves out of the shadow. Okay, same thing here. If the Moon is orbiting in this direction, okay, we're going to have a situation where I got the sun casting all this light, got the Earth. Okay, I've got the Earth, and then the Moon moves down into the pathway between the sun and the Earth, creating the shadow. And so when it comes to a solar eclipse, the best viewing is wherever this umbra path is going to be as it goes across the Earth. On a lunar eclipse, it has to pass through, obviously, when you're at nighttime. Okay, because you're on, whoever can see it is going to be on the opposite side from the sun. So that's the idea of, let me back up. So there you go. That's your for this section. And I know it was a bunch. I'm right at an hour. So it's possible that we break this up into two parts. We'll see how it goes. But anyway, we'll figure all that out at a later time. But again, thank you. Lots of good stuff here. I know there's lots of stuff, but lots of great stuff. I mean, we talked about how the combination of the orbit around the sun, the rotation on our axis, and the tilt causes the seasons, and the orbits causes the calendar, or helps us to figure out a calendar, the rotation, our clock system. We talked about tides. We talked about phases of the moon, which I love, and of course eclipses. Love talking about those. Love watching simulations. and there's some great ones, and I'm sure in class we will do that. But it's the idea of seeing it and knowing that you're seeing what's happening out there in space, which is pretty awesome to think about. So with that, we will begin the goodbye process. But again, thank you for watching this. Thank you for taking the time with the notes. You need to go back and grab anything, be sure you do. Make your drawings. Oh, I should have said on this, hey, be sure you get me the eclipse. There's just the 3 planetary bodies, and draw the lines here, the umbra, the penumbra, piece of paper, whatever, sketch it out, pencil, doesn't matter, but get that sick stuff. So just kind of really take care of drawing these 2 pictures out in a pretty good fashion. So with that, look forward to seeing you in class, and until next time, we will say goodbye.